All right, today we'll be talking about standard 2.4, which is basically solving word problems involving acceleration, position, distance, and displacement. So the steps that we use to solve problems, we call it Dguess to shorten it to help you remember. So the D stands for drawing a diagram of the situation. That's going to be where we start. G, we want to write down the important given information. U, we want to write down the unknowns of the problem. E is choosing the correct equation because we'll have a bunch of different equations to pick from. The first S is for substitute. So we are going to substitute our given values into that equation that we pick. And then finally, the second S is to solve the problem. So that's where we're showing our work and then writing our answer with units. So Dguess, draw, then we write down the givens, then we identify our unknowns, then we choose an equation, substitute, and solve. So here's what this looks like. If we have a problem here where a trucker is driving on the freeway at 20 meters per second, they see a traffic jam up ahead, they are going to slow down. How far does the truck travel in 3 seconds? So we are going to start with a diagram. So our diagram would just look something like this, pretty easy. We have a truck, it's going 20 meters per second at the start, it's slowing down as it moves. After our diagram, we move on to our givens. So we want to try and identify the important stuff from the problem. Usually this means the things with numbers. So we see a couple different things with numbers here. We see 20 meters per second, we see slowing down at 4 meters per second squared, and we see 3 seconds. So this is all the important information from our problem. So we write those down and try and identify which variables they represent. So that 20 meters per second, that represents our initial velocity. Our acceleration here, is that 4 meters per second squared. Notice that it's slowing down. So since we're saying initial velocity is positive, we can say slow down is just negative, because remember our signs don't match when it's slowing down. So initial velocity of 20 meters per second, we'll just assume it's going to the right. Acceleration then is -4 to make it slowing down. And then that 3 seconds there, that just represents time. A helpful thing is to look at the units. So meters per second, I know that's velocity. Meters per second squared, I know that's acceleration. And seconds, I know that's time. So looking at the units also helps identify what each thing means. After our givens, we move on to unknowns. So in this case, we're trying to find out what is the problem actually asking us to solve. So if we look at it, we see it's asking how far does the truck travel in 3 seconds? So that means we're trying to find out just how far it goes, which is the distance. Or in this case, we can use displacement because that's what shows up in our equations. Now we need to pick out an equation. So we have our givens, we have our unknown, we know what we're trying to solve for. We need to pick out an equation that will let us solve for our unknown. So we take a look at our list of equations. We want to rule out anything that has stuff that isn't on our list right here. So that automatically rules out all of our unit 1 stuff right away because we have an acceleration. So we need to use an equation that has acceleration in it. And now we want to pick out one where we can determine a displacement. If you take a look, we have this bottom one here where we have delta x, but that would require us knowing the final velocity. And since we don't have our final velocity, we won't be able to use that equation. But instead, we can use this top equation. So it doesn't specifically say delta x in it, but just remember that displacement is change in position. So if we just say like the initial position is 0, or if we do a little algebra, we can use this top equation. So here is what that looks like. If we just subtract that plus xi over to the other side, and now we have a change in position here in that equation. So really, a lot of times when we look at this equation, we can do one of two things. We can assume the starting position is 0, or we can just remember, oh, it's just change in position. So that's where our change in position comes in if we just move it over to the other side. So really this equation right here and this one, they're the same equation, just different forms. So if we only care about how far something goes, the change in position, and not like the final position, we can just use this form of that equation where we move the x over to the other side. So that's what we're going to be doing. Now we get to the substitution step. So we picked out our equation, and we are just going to put in our numbers. So you can see here, we have acceleration, we have time, we have initial velocity, we have time. So we have everything in this equation that we need to solve for our change in position. So we just substitute our values in. When you are doing your work, you want to show this as two separate steps. So write down the equation you're using without putting any numbers in, and then put your numbers in before you start doing work. So I would write both of those things down. And finally, we get to the solution step, or solving. Now we're just showing all of our work. So this is where we show our math. So if we look, we're just plugging stuff in. So acceleration is -4, time is 3 seconds, initial velocity is 20, time is 3 seconds again. Simplify it, and we end up getting 42 meters for our distance. When we have objects falling, so sometimes a piece of information won't be given to you, it's just assumed that you know it, and that is the acceleration due to gravity. So objects on Earth will always fall with the same acceleration if there's no air resistance or any other factors going on. So all things being equal, any objects on Earth will fall with the same acceleration, and that acceleration is -9.8 meters per second squared. That is so important in physics that it gets its own variable. It's called g. So we just use little g, and anytime you see that in physics, it just represents -9.8 meters per second squared. So if you look at this animation here, you can see a bowling ball and a feather. They're being dropped in a vacuum, and you can see they fall at exactly the same rate, so they have the same acceleration as they fall. This only happens in a vacuum, but a simplification we make in physics is we'll just say, well, we'll just assume this is happening in a vacuum, otherwise the math gets a little too complicated. If you want to see like the source for this, there's this video here in the notes, so you can watch this video in the notes. It's a short, like 4-minute video that just explains this a little bit more, but just for some proof, here you go. Feathers falling next to a bowling ball, same acceleration because it is in a vacuum. So here's what a free fall example would look like. We say a skydiver is jumping from a plane and they begin falling downwards at 5 meters per second. How fast are they moving after falling 100 meters? So as always, we want to start with a diagram. So here's my diagram. We have the skydiver. They're starting 5 meters per second falling downwards, 100 meters downwards. They are then going some unknown velocity that I'm trying to find. Next, we want to go and try and identify our givens. So notice it's falling downwards at 5 meters per second. When we put that in an equation, we need to keep track of that downwards as this negative sign right here. So remember, -5 meters per second means down in this case, or left if we're moving right and left. So we need that in the equation to get the right answer. Our displacement, so after they fall 100 meters, again, remember they're falling 100 meters downwards. So we have -100. We're not using positive 100 here. And then this is why we talk about the free fall example. So it doesn't specifically say the acceleration, but anytime something is moving through the air on Earth, just like falling, it gets the acceleration of -9.8. So that is going to be an assumed value that you know to use. Acceleration is -9.8 meters per second squared when something is falling on Earth. Next up, we want to identify unknowns. So from this problem, we don't know time, we don't know final velocity. Specifically, we're asking how fast will they be moving? So final velocity is the one we want to focus on. So we want to find final velocity in this problem. So we look at our equation list again, and we want to rule out, first up, anything that doesn't have acceleration in it, because we know we're going to be using acceleration. And then we want to try to pick out our equation that will let us find final velocity. So if we look here, go back for a second. If we look here, we have a couple options that have final velocity in it and acceleration. It could either be this one right here or this one right here. So this first one, v final equals at plus vi. We know vi, we know a, but we don't know t and we don't know vf. So we wouldn't be able to use this equation to solve it. If we look down here, final velocity, we know initial velocity, we know acceleration, we know displacement. So we have everything in this equation except what we want, which is final velocity, which is why we use that equation. So from here, we want to substitute our values in. So again, when you show your work, you want to show the equation you're using, write it down without putting any numbers in yet. Then we put numbers in for our next step. Don't try to combine these steps, do them as two separate steps. So initial velocity is 5 meters per second, remember downwards, so we plug in -5, and then acceleration, because we're in free fall here, is -9.8, and then our displacement is -100. Then we try to solve this. So we just simplify, and we end up getting that final velocity is the square root of 1,985. So remember, square roots, that could be two different answers. It could be positive 44.6 or negative 44.6. So we need to think about the context of this problem to pick out which one it is. In this case, since they are falling downwards at the end, we know we want to pick the negative 44.6 as the correct answer. So we're picking negative 44.6. And then when we write that, we could write that as either negative 44.6 meters per second or 44.6 meters per second downwards. You don't have to say both. You can just pick whichever one you think makes more sense or whichever one you are more comfortable with. So we'll always assume negative just means down or to the left, just in the negative direction. So a couple helpful hints as we solve these. There's too much variation in these word problems that we do to give you, like, here's step one, here's step two. So think of these like Dguess as more general guidelines. We're not always using the same equation. We're going to be picking out different equations. We need to just basically learn kind of the general process, the general approach to solving these problems. When we follow these steps, it will be very helpful in the future. So some problems might seem pretty easy where it's like, oh, I can just multiply these two numbers and write my answer down. That would be easier right now, but in the future, we want to set a good foundation. So by following Dguess, we can do harder problems in the future. So some of them might seem easy right now, but if we practice basically good problem solving habits now, it will help out in the future. And then if you look at the first example, distance and displacement are kind of interchangeable in the equations. We just want to, when we look at equations, basically say, like, if you see a delta x or something that can be used for distance, just look at what the question is actually asking for. And if it's asking for a displacement, then we want to include a direction at the end. So up, down, right, left, positive, negative, something like that. A couple important reminders. Remember that displacement, delta x, is just the final minus the initial positions. So like we did in that first problem, we can take this equation, 1/2 at squared, that whole equation, and we can rewrite that as delta x equals 1/2 at squared. So again, if we just subtract this xi from both sides and we basically move it over to the left, then we're left with xf minus xi, which is just displacement, which is this substitution right here. So this is another form of that first equation. Same thing, but this one just lets us find basically displacement, how far did it go, instead of like a final position. When we use these problems, or when we use these equations, the directions are really important. So we want to make sure if it says an object moves left at 5 meters per second, then you have to use -5 in the equation. If you don't, you'll get the wrong answer. So it's usually helpful to look back at your work, like look at your final answer. If it says something, well, this object is moving left and slowing down, if it starts moving at 5 meters per second and you get a final answer that's like 7 meters per second, you probably made a mistake, and 9 times out of 10, it's because you missed a negative sign in there somewhere. So always double check your work. Does that answer make sense? If something's slowing down, it should end with a smaller or a lower speed. If it's speeding up, higher speed. Acceleration, remember that slowing down, if you see slowing down in a problem, it doesn't automatically mean negative acceleration. Only if something is moving to the right is it slowing down with a negative acceleration. If something's moving to the left, remember its velocity then is negative and its acceleration is positive. So we just need to pay attention to that. Remember what we talked about earlier this unit. And finally, remember, this is just general math. You can only solve an equation if there is exactly one unknown in that equation. If you have multiple unknowns, you won't be able to solve it. So if you feel like you don't have enough information to solve a problem, like I think it should be this equation, but I need this other thing, remember, you're either using the wrong equation, you are missing a given from the problem, and a lot of times that could be that if it's falling, the acceleration is -9.8. Or you need to solve for that thing first. So let's say you need to find time. Maybe there's a different equation you can use to find time. And then from there, you can plug it into the equation that you want to use to get your final answer.